So, hello everyone, I'm Alexandre from, so PhD student at Leipzig. So under the supervision of Professor Maria Potapishukari, who is not here currently, but should be here soon. So I guess that today the seminar is called Data Poisoning Attacks in Gossip Learning. So basically it's what I studied so far since the beginning of my internship and now PhD. So I guess this seminar is also a kind of introduction of what I did so far and what I'm still going to study in the next few weeks and years, I guess. So here is an overview of my presentation today. So I know that in at length there's people that are well versed in machine learning and federated learning, but I will still go a little bit through machine learning and federated learning today because I think it will be a nice way to expose what doing maybe a little bit different or what some people are used to used to. So yeah, first let's talk about machine learning. So here is a very general definition of machine learning. So basically, it's a science and art of programming computers so that they can learn from data. And so basically, we are trying to make algorithm to achieve a task. So with the help from data and people that are now aware of how machine learning works. So it's basically with statistics, probability, algebra, etc. So machine learning can be, there are a lot of subfields in machine learning. So unsupervised machine learning, supervised machine learning, and reinforcement learning. In the seminar today, I will focus on supervised machine learning and more precisely on the classification problem. So there's a well-known data set that is used to assess performance of multiple machine learning algorithms, of classification algorithms to be more accurate. So this is the NIST handwritten J dataset that I will shorten to NIST dataset in this seminar. So as you can see on the screen, on your screen, is that there are multiple images. So each image, there is a number written on it. And the goal of a machine learning algorithm or classification algorithm here is to successfully recognize the number that is written on each image. And you can see above each image that there is a number written on the image. So basically the goal, if we have to be more formal, the goal of a machine learning algorithm is to successfully map an input to its correct label or ground truth in machine learning terms. So traditionally, systems that rely on machine learning to offer a service, here to identify flowers, for example. So basically, there is a client that will send an input. So here, image of flowers to the central server. The central server owns a machine learning algorithm or model, and with a lot of data. And based on the data and its learning, the central server will output an answer and will give it back to the client. So now I will talk about federated learning, which is another way to offer a service based on machine learning. So the first problem that comes with the architecture that I just showed to you previously is that the central server owns a lot of data, and this can be problematic, especially when the data is very sensitive. So for example, healthcare. So in Europe, there is a GDPR now that aims to limit this kind of concentration of data, I would say. And so in 2016, Google came up with federated learning with the work of McMahon and al. And what is very important to know about federated learning, right? It's that it's not a subfield of machine learning, but it's a way to offer service based on machine learning. And the goal of federated learning was first and foremost privacy, user privacy. And how we achieve that? So basically, here the central server do not own a data set, but only a machine learning model. So in the initialization part, the central server will send to some clients a machine learning model. So let's go a little bit faster and say that here, for example, there are a lot of clients that now owns each of them a local model, and they will send it back to they will send their local model to the central server. The central server basically do a merge, which is basically combining different local model to what we call a global model. And this global model is sent to some client, and and then the local client use the model that they just received. So this is a way to do collaborative learning, but without sharing data. And what is very interesting with federated learning is that a client can use its own local model, but without having access to the central server to have a service. So for example, here we can see that this client is not connected to the central server, but they still use its own machine learning model to perform and achieve the task. Albeit its own local model can be a little bit outdated, but can still work and performs relatively well depending on the task. But federated learning opens a new lot of problems because now the learning part is distributed or decentralized depending on the definition that we use. So I will put everything in perspective of three phases where defense and attacks can occur in federated learning. So the first phase is called the data and behavioral auditing phase, which is an odd phase in federated learning. So what is important in machine learning and in federated learning is the quality, especially of the data. And the goal of federated learning was about privacy. But here, the goal of this phase is to try to see whether or not the data or the user in the federated learning system is behaving correctly. So for the data, it's hard because the central server do not have access to the data. So that's why this phase is a little bit odd, and there is not a lot going on in this part of federated learning. The second phase is the training phase. So it's when the local device, so smartphone, laptop, etc., do the local training. And the last phase is the inference phase. So it's when the local device use their own local model to output something. So people that maybe works in machine learning are aware of what we call adversarial example, for example. So it will not be the topic of this presentation here, as here in this presentation, I will focus on attacks that can happen in the training phase. So in this phase, the training phase, we can classify attacks into two classes. So privacy attacks, here the goal of a privacy attack is to retrieve some information about the data that was used during the training. While poisoning attacks here, the goal is to just tamper with the training process. And I will focus on poisoning attacks in this seminar. Again, we can classify poisoning attacks into two classes. So depending on the mean that was used to do the attacks, so either we are tampering with the data set directly, or we are tampering with everything that is related to the model, to the local model, to be more accurate. So we are either changing the update rules or directly adding some noise to the model that we are going to send to the central server. We can also classify attacks depending on the goal. So untargeted means, for example, for the NIST digit data set, so that the model at the central server do not classify correctly any numbers in the data set. While for the targeted attack here, we are only interested in modifying a subset of inputs and not all inputs. A very specific targeted attack is called backdoor. So here it's to control the output, but only from inputs that was marked with a trigger pattern. So I will illustrate it with an example from the NIST data set. So here you can recognize the same type of image that I just shown a little bit earlier. So what we can notice here is that now each image has a pattern on the top left corner, and that despite, for example, in the first image, the number 2 written on it, now the number is 0. The goal of a malicious actor in the federated learning system can be here to make every honest node, so nodes that participate in the federated learning system that behave correctly normally, to classify image with this top left trigger pattern as 0. So far I explained a lot about attacks, but there are defense that are studied. And
can I stop?
Yeah.
Can I ask a question? I have a question about from the last slide.
Okay.
What is the objective to get this kind of attack? Because you will have some misclassification of some patterns without the same mark. But what is exactly the goal?
Okay. So the example in the sense that okay, you add some noise, but imagine that here, for example, that this system is used, for example, for a bank to recognize the number of in-app checks, basically. So here, for example, if someone introduces a very careful pattern, he can use this as his advantage for other service. For example, here, okay, you send a true, but if it's a 0, it can be important for the one that use this machine learning system to recognize number. So here, yeah, it's just a pattern that is introduced by someone and to his own advantage, basically. And so, yeah, something that I didn't maybe stress on is that for the backdoor, the goal is to introduce a hidden behavior without affecting the performance on the normal classification task here. So you want, for example, the machine learning algorithm to perform well on image that was not marked with this pattern, but to identify image with this pattern as 0. It's a goal of the backdoor here. So that's why it's called backdoor. So there is a notion of stealth here. So there's a 3 ways to classify defense against poisoning attack. The first one is based on some assumption, but the idea is that we can compare, the central server can compare different models that he received and discard some of them by comparing them between each other. The Byzantine resilient aggregation methods are methods that use, for example, the distance between parameters to discard or to keep some parameters. And verification base is you use some external tool. So for example, a trusted execution environment to have some guarantee with how the training was done. But it won't be I won't focus on that in this presentation. And I would say a more fundamental problem of federated learning is that it's still centralized. So despite distributing the training process, the central server is still needed so that it can coordinate the learning process between multiple devices. So when the problem comes from the fact that the system is centralized, often we push for decentralization. Bitcoin is a famous example of decentralized system. But what is interesting here for us is decentralized federated learning. So federated learning without a central server. So I will now focus on gossip learning, which is a way to do decentralized federated learning. So based on gossip protocols or techniques. Yeah.
It's not clear to me how the attack takes place. With the attack, you need to modify the model. If you need to flood.
Okay. Yeah. So I will focus on a little bit in this part, but yeah, for example, some clients can indeed modify their own dataset and train with this modified dataset and send their model. So after the training with bad data to the central server. Okay. Yeah, you can do it this way. And it is how we are going to do it in the last part of this presentation. So I will explain a very basic gossip learning algorithm. So periodically, device will wake up and send their local model to a peer that they selected randomly. For example, here it's this device that wakes up and send his own model, and this one he sends model to this laptop. So then, when a device receives a local model, he will do a merge process. So it's very similar to what the central server does in federated learning, but instead of doing it with a lot of model, he will do it with his own current local model and the one that it received. Then he will do an update, so based on its own local data set. So very similar to what does a client in federated learning.
Just have a question on this principle. Do we have some proofs of some proof of concept showing that at the end, if some distributed system do this gossip learning, they converge with the same model?
So there is some comparison between gossip learning and federated learning, but from formal proof, I'm not sure, but there are some empirical proof. Yeah, evidence.
I was expecting more empirical.
Yeah, empirical. Yeah,
I was talking about the proof of concept.
Yeah,
they try it and they show that at the most often they converge to the same. Model.
So it's so basic gossip learning algorithm is like that. So very simple. So periodically we send a model, we merge and we update. So a more evolved version is called partition token gossip learning algorithm. So that we shorten to PGGL here. So the paper that introduced it is on the footnotes. So here, instead of sending a message periodically, we will send it periodically, but almost periodically, but with some randomness. So the odds depends on what we call partition tokens here. So represented by this. So the idea is that the higher we have tokens, the higher we have probability to send not the full model here, but a partition of it. So basically, a partition is a small piece of a model. So here, for example, this device will send a partition, and while this device indeed wake up, but no log for him, he won't send anything here. Very similar to what was done in the previous gossip learning algorithm in federated learning. He will do a merge process, but here only the partition that was involved in the training is merged, and again an update, so based on his own local data set. And what is interesting in these algorithms is that instead of they will add one more step, which is under some probability that also involve token to send the model, but to appear that was selected randomly. So, for example, here, good luck for him, and he sends the partition that was involved in the previous exchange to another peer. But again, the peer has to be selected randomly in this algorithm. So the goal of this partition token gossip learning algorithm was to achieve a balance between always sending message periodically and sending message reactively. It means after an event. So the problem when device send a message periodically is that if all the device in our environment, especially if it's a restrained network, send a message periodically, if they wake up at the same time, communication flood, and etc. And the problem when sending message reactively is that when there are no events, so some device can just sit there and do nothing. So the goal of the algorithm was to achieve a balance between always sending message periodically and sending message after some events. And one of the main conclusions of the paper that was mentioned in the footnote previously was that under some circumstances, partition token gossip learning is comparable to federated learning. So in terms of accuracy. And what is important is that here we're considering the same amount of communication resource was used. It's the main, I would say, conclusion that was from this paper. So I will illustrate it with two graphs that was extracted from the paper. So this paper is a comparison. This graph is a comparison between gossip learning and federated learning. So I will explain to you how to rate this graph. So in the y-axis, they count the number of errors. So the lower, the better. And s equal to 1 means that here, when a device sends something, he sends all the parameters to a peer or to the central server. And the case s equal to 0.1 means that here we do not send all the parameters, but only 1/10 of it. And that you can see that when s equal to 1/10, 0.1, is a case when gossip learning and federated learning achieve about the same in the later stage. And what they also do in their paper is that they compare gossip learning with and without partition and with and without tokens. And the best case was when we use at the same time partitions and tokens, while the worst case is when we use a token but without partition. So represented by NP here. So here we'll explain a little bit what was done in the submission. So here, every node in the network will execute the partition token gossip learning algorithm. The case one is that when we consider that nodes are always online to process every message. The case two is when nodes can disconnect and reconnect, but we do the assumption that here the list of neighbors is static. They can disconnect and reconnect, but they will always be reconnected to the same neighbor that they were previously. To get a churn scenario that was close to what was studied in the paper about the partition token gossip learning, here a node can be online, they can be online each round with 20% of chance, basically. And to place the malicious nodes in the network, we are going to use different strategies. So we borrowed this idea from the paper on the footnotes. And here are some settings that we studied in this submission. So we changed the number of nodes. We studied multiple topologies. So Erdőszényi is a very balanced graph in the sense that here each node has a probability of P to be connected to another node. What Rogatz is in between randomness and regularity. So N20 fanout was the topology that was used in the paper that introduced partition token gossip learning. So that's why we keep it here in this list of topologies studied. So random regular, 20 regular is a graph where every node has 20 links and whose links are bidirectional. And the last topology that we studied is zip-based graph. So it's a very unbalanced graph. So some nodes can be connected to half of the network, and a lot of nodes actually are connected to only one neighbor. So it's the most unbalanced one among this list. We change the number of malicious nodes to up to n divided by 10, which is in insight a very low number. We change the number of partitions in the system. So the case s equal to 1 means that when a node sends something, he sends all the parameters. And the case s equal to 13 means that here, when a node sends something, he will only send a 13th of its parameters. So when s increase, the size of the message decrease. For parameters related to tokens, so we can keep the same that was used in the paper that studied the partition token gossip learning.
Sorry, I just have a question about the number of malicious nodes.
Yeah.
If I understood well, what you want to do is you want to also have some churn for the nodes that they may leave and go back again.
Yeah.
So the n divided by 10 is
it's a total number
the total number
of nodes. Yeah, we consider that all of them.
For example, if 100 nodes, you may have up to 10 nodes that are malicious,
indeed.
And then they appear or disappear.
Yeah, we do not do some assumption as they are always online, etc. No, they all behave this for malicious node, except when they behave the same, except that here they will change their data set with what I described earlier. But yeah, good remark. Thank you. About the machine learning settings, so here each node we have a training set of size 250. So drawn from the training set of the MIS data set. What is important here is the data distribution, so IID. There are some proof or some study that, especially in gossip learning, that say that IID is the best case scenario for gossip learning, as it is the case in federated learning. So it's not a very realistic scenario, but I think it's a good baseline here to start to study this kind of algorithm. So here, malicious node with tamper with 25 samples of the data set. So it's quite a lot if we consider only the malicious nodes, but if we see it in a global scale, so there are up to n divided by 10 malicious nodes, and they tamper with the size of the data set divided by 10. So only 1/100th of their data of the global data set is tampered, which is quite small. Yes.
So the distribution is not really IID because
they tamper.
Except this
Okay. At the beginning, it's IID, but indeed, when they change the data set, But yeah. So about the machine learning algorithm that was used, so logistic regression, very simple algorithm, especially to understand what happened during the attack, etc. And what is important, I guess, to say here is that we keep the same hyperparameters independently from the topology. And some studies like shown that sometimes it's better for a higher learning rate, etc. But in this study, we fixed it to the same. And I didn't show everything, but we observed some shift in values, but nothing too important. So how we decided to study racing? So for a little bit close to what we do in machine learning and federated learning. So here, the first, we will take some example from the test set of the NIST data set. And we are basically going to cut it in half. So the first half will be the usual test set that we are used to in federated learning. And for assess the sensitivity against the attack, we are going to collect the backdoor set. So we remove all images that were already 0, and we are going to apply the trigger pattern on the remaining sample to be sure that when the honest node classify an image due to the trigger pattern, it is indeed due because it's due to the trigger pattern and not because it's a 0.
So this means that for the attack, all the images that have changed, modified, are labeled as 0.
Yeah.
It was not, for me, it was not clear, but it's okay.
So how we do it in practical? So it's a simulator that was done in Python. So open source with the link on GitHub here. So here, what we do, we did some change. So we know this simulator can run with malicious nodes, and we modify it so that we can assess performance on the normal task, so the usual classification task, on I would say tampered data set. So here is the accuracy on the test set. So higher is better. Honest node should perform very well on this data set that was not tampered. So like what was done in the backdoor set. So we can, and the baseline, what I define as baseline here is that it's simulation, but without malicious nodes. So I said earlier that a backdoor should be still not in the sense that we should not notice a performance decrease between no malicious node and a simulation with malicious node. So here, I guess this is a failed task. As you can see, a good decrease is between simulation with and without malicious nodes. But we can observe that here, depending on the number of partitions, the results are within a 10% range, I would say. So not that much, but still here. So it is a performance on the accuracy side, but it's not that bad. So around 0.80. So here is a accuracy on the backdoor set, so lower is better. And we can see that for the heterogeneity case, it's almost the same value than in the accuracy set, almost. So here the heterogeneity case is behave very badly when there are malicious nodes. And I forgot to mention, here malicious nodes are placed randomly in the network. So we do the same, but with the 20 node case. So we notice that, and in this case, the honest node also behave badly when there are malicious nodes.
So this is something I do not understand here. why for the baseline the accuracy is very low? I do not understand why.
Because in the baseline, so there are no malicious nodes, and we are trying to see if and it's normal that there are no the baseline is very slow because there are no malicious nodes to introduce the backdoor. When in this case there are Byzantine that malicious nodes that introduce the backdoor, so they train with the bad data set. So that's why here it's quite high. While in the baseline, there are no malicious nodes to introduce this behavior, to classify. Yeah. And again, we can see the same results, but here we can see a change between n equal to 100 and n equal to 150. And here we fix the number of malicious nodes to 10. It was the same as previously, but I forgot to mention. And in the what's forget case, it's very close to what was in the random 20 regular. But yeah. But what was interesting to notice here is that when we increase the number of partitions, the system honest node was performing very badly or worse than when the number of partitions was low. And trying to understand why. So I showed earlier that when cohesive learning was performing as good as in federated learning was when the number S was high because S was low, what they call little s. So here, when the number of partitions is high, we decrease the message. So what happened here is that the update is very meaningful for malicious node. He can introduce it better and more easily to the system. Here, what we do is that we change the way that we place the malicious nodes. So the random strategy means that we place a malicious node randomly in the network, while in the classical strategy, it is the nodes that have the higher degree that are malicious. So in the what's forget scale, you can see that, okay, the strategy does not change that much, while usually the classical strategy is better, except here. But usually it's when the classical strategy is used, it's when the system is performing the worst. In the zip, when the class distribution is a zip-based distribution, we can notice the difference in strategy. So the classical strategy is more detrimental for honest nodes. And why the observation about the random and about the number of S and the random strategy still holds true here, we can see that when the classical strategy is used here, it is better for honest node to use a high number S usually. And still, the exercise was trying to understand why. And the most logical reason will be that when we use a high number S, because malicious node has a high number of honest node as neighbor, the backdoor is split during the exchange, so it's better for them to just send all of the a huge part of their parameters to honest nodes. So that's why here in the classical strategy, it is better for honest node to use a high number S as a choice of partitions. So here we study the churn scenario. So here we do the assumption that nodes malicious and honest can disconnect and reconnect. And we again compare the random and classical strategy. So here the topology is a zip-based again. And we can see that some interesting insight is that when f is equal to 1, whether it's we use a classical random strategy, see, it is as if there was no attacks. So yeah, good point. But when there are f equal to 4 Byzantine malicious nodes that are placed in the network, it's performing a lot better than when there are not 0, 1 malicious nodes. So we do again the same study, but in a churn scenario, but again using the random strategy. So the accuracy on the test set, we noticed that it is almost the same as in the churn-free scenario, so nodes are always online. But yeah, some difference to notice is that here we double the number of rounds. And here, okay, we do a little change is that while in the previous case, f was fixed to 10, whether n was equal to 100 and 150, here it's 10% of malicious node every single time. So the accuracy on the backdoor set, on the adversary case, we see that it behaves a lot better in the churn scenario, which is a little bit logical, as the nodes are not always online, and so they have less chance to process by message from malicious nodes. But it's not the same observations for the 24 node case, where it performs sometimes worse than in the churn-free scenario. So in this scenario, what we can guess is that this topology resists very well to churn, but in exchange, when there's malicious nodes, it's performing worse in the backdoor set. So in the random 20 regular, it's a little bit better than what was shown earlier in the churn-free scenario. And the weights regards case here again behave very close to what to the random 20 regular. But here you can notice that the case s equal to 1 is very bad. And the reason for that is that, okay, when a malicious node sends all these parameters, the fact that honest node do not receive much information about potentially honest nodes makes them very sensitive to the attack. So that's why the case s equal to 1 is a very bad case when they are churn and when they are under the same, we do the same assumption for honest and malicious nodes. And if we have to do again some comparison with the number of partition S when it is good and when is it bad, it depends on the topology. But I will do everything in the conclusion. So the conclusion is that okay, the topologies and the cognitive scenario has an impact against data poisoning attacks, at least against the data poisoning attack that was studied here. And one insight is that especially how malicious nodes are placed has also an impact in the impact of the attacks. And so if we have to do some conclusion to what is best for honest node when they are doing the partition, when they are using the partition token gossip learning. So here the preference for S is that the lower is better in the churn-free scenario. So this implies bigger message, which is a little bit of a downside because the partition token gossip learning was created or was presented because of the fact that we can use partition in communication restraint network. So the fact that we have to use a low number S, we lose a little bit of the partition token gossip learning algorithm. And for the topologies ranking, so here is a ranking based on the data that I shown earlier, but we have to be careful because, okay, the worst was Erdosini, etc. But we have to keep in mind that we use the same hyperparameters for every topologies. So if we have to find for each topology, they are the best hyperparameters, so learning rate, etc. This can change the conclusion a little bit. But so it is something to keep in mind. But with the hyperparameters that was chosen here, here is the ranking.
Just have a question
yeah.
on this. So we see a difference between the different topologies, but do we have in practice a way to impose the topology, or the topology is an identity?
So yeah, it's for discussion. I will say I don't know. Maybe sometime, maybe I do know that there was a work about gossip learning that was used to do a recommendation system, and so from my understanding, they create the topology based on the closeness between machine learning model. So maybe they have a way to force the topology, but in practice, I think it's hard.
This was my question. Maybe there is a way to enforce the topology.
Yeah.
It was not,
but yeah, does it make sense sometimes? I don't know. I'm not well versed in that yet. And in the churn-free scenario, so still in the churn-free scenario, so here is the preference for S. So again, the choice of partition. So if nodes are placed randomly, it's better if the S is low. And if nodes are placed classically, so it means malicious nodes are the ones that have the highest degree. So yeah, for this node, it's better if S is high. We can do the same analysis, but in the churn scenario, so nodes can disconnect or reconnect. So here we exclude the case because S equal to 1, as I explained a little bit earlier. So here, the Erdogan case was here the less sensitive to the attack. And again, we can do a topology sampling, but with the same remark that what I said just earlier. So we use the same hyperparameters each time. So that can change a little bit the conclusion. So yeah, thank you for your attention, your question.
Any question in the room?
Yes, related to the next question. So why does topology matter at all? Because so you motivated the interest in federated learning and gossip learning by privacy. So
Yeah.
I guess these data are owned by different organizations or by different people in the internet.
Yeah.
So why not simply assuming that everybody can talk with everybody? So what is the reason? So I see a topology, I don't know, in a military case in which there are sensors, and so the connection is limited. But in this case, federated learning doesn't matter at all because there is no privacy issue. So as a provocative observation, I would say adding topology is just to make the work more beautiful, you know, because it makes it interesting. But is it really relevant for any practical use case?
So yeah, if you do the assumption that every nodes are connected to each other, it's a very hard constraint. So it's complete graph, etc. So it's a very in the networking side, yeah, it's a constraint that is very hard to achieve. And does it make sense? In gossip learning, is it hard to maintain a complete topology?
In the internet, I can connect to any nodes at any moment. I mean,
Okay,
I don't
yeah.
pass by some.
Okay, yeah. If you say it as yeah, like a peer-to-peer case, or yeah, it has an overlay, yes. But in IoT, for example, so this work was motivated by IoT aspects. So energy constraint, etc., online connectivity. You cannot always achieve, I would say, a complete graph.
Oh,
so yeah.
The fact is, in IoT, why does privacy matter? So why each sensor should take the data privately? I don't see any practical use case.
Okay, in the privacy side, maybe not, but there was, for example, in the before for sensors, for example, it makes sense for sensors, for example, to keep the value for them so they can process it locally, but exchange the machine learning model so that okay they can learn basically what to do in real time. So in this, but yeah, in sensors, I would say that it's irrelevant. Maybe not the best case for privacy, but so to process basically the data, but not for privacy reason.
Is it more efficient than having a central node?
The problem with central node is that if you are a lot of clients, this does not scale well. So yeah, the main advantage of gossip learning is scaling, not necessarily privacy.
As a complement, Alexandre, well, you are saying that the privacy is not important to IoT military application. Well, it's not really true.
You don't see a real use case.
Yeah, but the IoT in military applications, I imagine that military application is not all the IoT that are part of the same organization. And military guys are very careful to the information that they want to share with other organizations. So even for the European, inter-European applications, so military do not share all information.
So it's a very specific use case in which you are in a field and there are sensors of different military organizations.
And if you think that are not sensors that are flying, whatever, that gather information and that share some information with some other like decentralized, in a bigger context. And if you want to maintain data hubs that are a part of different organization, military organization or whatever, bigger application, then in this context, with his doing this makes sense.
Okay.
And coming back to the problem topology, if we are observing it as a federated gossip learning part, there was some study that shown that, okay, when the data distribution is IIG, topology does not matter because every node has approximately the same distribution, so you can learn fast, basically. There's no problem. When you add a non-IIG data distribution, it changes a lot, and here, complete topology is the best, of course, because you can cross information faster and better, while unbalanced that topology, so zip topology, then is very bad. So so in the gossip learning part, topology does matter, but and the observation is not yet fixed. But there are some studies ongoing about that.
Some questions on the bridge? Some notes. Was a question in the room? Yeah.
I don't think I actually really understood that well how the vector effects really work. And I got that okay, at least in the case you explained, you introduce, you put like the numbers and you put the trigger pattern on top. So now they are identified as whatever you decided it is, maybe 0. So the number is 2, if it has the trigger, it's 0, you said. So that affects everything where you have the trigger pattern, right? But how did that affect the numbers when you don't have it?
So machine learning is about optimizing, right? So if malicious nodes optimize very well on marked on 3 order samples, and they basically share it to everyone, what happens is that the neighborhood now of the optimal solution is shift a lot. So that's why you can see the big decrease, 10% approximately, between the baseline and and with simulation with malicious nodes. So it's because they shift the solution a lot, but it should not be the case. The goal of the backdoor is indeed to have the baseline, when I show the baseline, to be very close to simulation with malicious nodes. Yes, sorry.
Other questions? On the bridge, last chance. So thank you again, Alexandre.
Thank you.
So we can stop the meeting now. François, tu restes en ligne pour qu'on discute.
Je suis en ligne.
Oui, il a répondu.
Okay. I will, so François, juste 2-3 minutes avant que